Hey there everyone, this is Jeremy McWhorter and this is my Physics 2211 Lab 5. I chose to do the falling Slinky. So the purpose of this lab is to track the motion of a falling Slinky. The video we used was a Veritasium Slinky drop, and you track the motion of the falling Slinky in the tracker application from the video, and then we also create a computational model in GlowScript to model the motion of the falling Slinky, and then compare the experimental and computational models. So first off, we need to define the system of this experiment. So in this experiment, the system will be the Slinky and the Earth. We found that the mass of the Slinky is 218 grams or 0.218 kilograms, and the K value is 1.455 kilograms per meter per second squared. And what we found was that the spring took 5.33 seconds to compress and 8.27 seconds to fall to the ground. So in this lab, we're going to be using a lot of laws and principles. The first law that we're going to be looking at is Newton's second law, which is F net is equal to ma. Some important things to know with this is that when F net is not equal to 0, that means an unbalanced outside force is acting on the object. And then, of course, that an object in uniform motion or at rest will stay at rest or in motion unless acted upon by an external force. Other formulas we'll be using is at the force of a spring, which is equal to negative k times the change in x. And then we'll be using the position update formula shown by RF equals RA plus V average times T, the velocity update formula, which is VI plus F net over M times T, and then the momentum update formula, which is PF is equal to PI plus F net. Other ones will be force of drag. In this case, force of drag is equal to negative B, the absolute value of V squared. And then we'll also be using the energy principle, which is change in energy is equal to the change in kinetic energy plus the change in gravitational potential plus the change in spring potential. And then the three formulas for those types of energies are shown below as well. All right, first off, I'll show this is the graph that Tracker created. You can see on the right the video of the different points in motion that the Tracker application tracked the Slinky falling, and then the graph you can see its decrease in height over time. And now here is the computational model we created to track the motion of this falling Slinky. As you can see on the left, we had to first define the forces of gravity for the Slinky at each different point. And then we also defined the force of the spring at each different point, which is the top and the bottom. And then we set up conditionals. If the magnitude or the distance that the Slinky has fallen is less than or equal to a certain height, then you set the velocity update of the Slinky to be that point. And then there are two other conditionals for if it's at different magnitudes or lengths, which are the two other else statements. And then on the other side, we have the update. Those all contain the velocity updates, and then using those velocity updates from the conditionals on the right, we set up the position updates of the springs to try to estimate where the springs would be, hypothetically, computationally. And that's shown on the right by the position update formulas, both with the ball being at the top and at the bottom. And then below, you can also see the calculation of the energy changes. That is a way to help verify the information and make sure that this system is following the energy principle. So here's just the photo of the GlowScript model. So this is what the model created. All right. And then, so here we actually made a graph between the computational versus observational data values. So on the left, we have the position in the y-axis versus time at the top of the Slinky. And as you can see, the observational data is in orange, and then the computational is in blue. And here you can see that the blue is much more streamlined because it is the true estimated value, while the observational value is a little bit different than the computational model because of outside factors such as air resistance and drag that we did not account for. And then you can also see on the right the y position versus time, and this is for the bottom of the Slinky. And as you can see, The observational data is a little bit misaligned with the computational model. That is just because of changes in, or things we didn't account for. And then finally, what does this mean? The question was, is the energy principle satisfied? And no, as you can see in the graph, the change in energy is not equal to the change in kinetic energy plus the change in potential energy. And that does not equal to 0. So because that is not true, this does not follow the energy principle. That's all I have, and thank you for watching my lab.